On the morning of September 15th, 2017, in a control room at NASA's Jet Propulsion Laboratory in Pasadena, California, a room full of scientists and engineers sat in near total silence watching a single line on a monitor. That line represented a radio signal traveling at the speed of light across 1.5 billion kilometers of empty space, the last heartbeat of a spacecraft that had been flying for 20 years and orbiting Saturn for 13 of them. Nobody in that room was looking at Saturn. Nobody could. Saturn was so far away that even the most powerful telescope on Earth could not have shown them what was actually happening out there in real time. What they were watching was a ghost, a signal that had left Saturn 83 minutes earlier, already ancient by the time it arrived, already describing a machine that no longer existed. And when that line on the monitor finally flickered, stuttered, and went flat at 7:55 in the morning Eastern Time, the people in that room, men and women who had spent decades of their lives building, flying, and listening to the spacecraft, broke down. Some covered their faces. Some hugged each other in silence. One senior scientist sat completely still, staring at the blank screen with the specific kind of grief that only comes from losing something you loved that never came home. What they had just watched was not a failure. It was the most extraordinary farewell any spacecraft has ever transmitted. And the story of exactly what Cassini sent in those final 91 minutes before it burned up inside the atmosphere of Saturn is one of the most remarkable chapters in the entire history of space exploration. To understand why those final minutes matter so much, you have to understand what Cassini was, what it had already accomplished, and why its ending was not an accident, but a deliberate, carefully chosen act of scientific sacrifice that NASA had been planning for years. Cassini launched from Cape Canaveral on October 15, 1997, carrying with it a European-built probe called Huygens that was designed to descend through the thick, orange atmosphere of Saturn's largest moon, Titan. The spacecraft was enormous by the standards of robotic space missions, roughly the size of a school bus, bristling with 12 different scientific instruments capable of measuring everything from magnetic fields to the chemical composition of gases to the precise gravitational pull of the planet it was orbiting. It took Cassini nearly 7 years just to reach Saturn, arriving in June 2004 after a looping path that carried it past Venus twice, past Earth once, and past Jupiter once, each planetary flyby using gravity to slingshot the spacecraft deeper into the solar system without burning extra fuel. When Cassini finally fired its main engine to slow down and slip into Saturn orbit, it became only the 4th spacecraft ever to reach that distant world, and the first ever to orbit it, rather than simply fly past. What followed over the next 13 years rewrote the scientific understanding of the outer solar system in ways nobody had fully anticipated when the mission was planned. The discoveries Cassini made during its long years orbiting Saturn were so consequential that several of them individually would have been considered the scientific result of a lifetime by any researcher lucky enough to be involved. The most stunning of all came not from Saturn itself, but from a small icy moon called Enceladus, a world only about 500 kilometers across that should, by all reasonable expectation, have been a dead, frozen, geologically inert ball of ice drifting silently around a distant planet. Instead, Cassini found it erupting. From cracks in its southern polar region, named the Tiger Stripes by mission scientists for their distinctive appearance, Enceladus was shooting enormous plumes of water vapor, ice particles, and organic molecules into space at speeds of over 1,400 kilometers per hour. When Cassini flew directly through those plumes on multiple passes, its ion and neutral mass spectrometer sniffed out something that stopped the scientific community cold: molecular hydrogen, pouring out of an icy moon at enormous rates. Molecular hydrogen is a chemical fingerprint. On a world with a liquid water ocean, molecular hydrogen in that quantity means one thing with very high confidence: hydrothermal vents on the ocean floor, places where hot water reacts chemically with rock and releases energy in a form that, on Earth, sustains entire ecosystems of life completely independent of sunlight. Cassini had found direct evidence that Enceladus, a moon of Saturn, a world receiving roughly 100 times less sunlight than Earth does, had a warm, chemically active global ocean of liquid salt water sitting underneath 30 to 40 kilometers of ice, with hydrothermal activity on its seafloor that could theoretically support microbial life right now, today, in our own solar system. Thomas Zerbashin, who was leading NASA's Science Mission Directorate at the time, said publicly that Cassini's discovery of ocean worlds at Titan and Enceladus changed everything, shaking our views to the core about surprising places to search for potential life beyond Earth. That was not promotional language. That was a working NASA administrator describing a genuine paradigm shift in how humanity thinks about life in the universe. Titan was the other revelation, different in character but equally astonishing in implication. Before Cassini, scientists knew Titan had a thick atmosphere. the only moon in the solar system with a substantial one, and they suspected it might have liquid on its surface. What they did not know was what that liquid was, what it looked like up close, or how deeply it had reshaped the moon's entire geography. The Huygens probe answered some of those questions when it descended through Titan's orange haze in January 2005 and transmitted images of a landscape that looked hauntingly like Earth. River channels carved by flowing liquid, smooth, rounded pebbles, clearly shaped by erosion, vast plains and distant shorelines. But the liquid was not water. It was liquid methane and ethane, hydrocarbons that stay liquid in Titan's extraordinarily cold environment of negative 179 degrees Celsius. Cassini spent years mapping Titan from orbit and discovered that this moon has a complete active hydrological cycle, essentially the same system Earth runs on water, but running on hydrocarbons instead. Methane rains from the sky. It carves river channels across the landscape. It collects in lakes and seas near the poles, the largest of which, called Kraken Mare, is bigger than the Caspian Sea on Earth. Titan became, because of Cassini, the only world in the entire solar system besides Earth known to have stable bodies of standing liquid on its surface. Not ancient, long-dried evidence of liquid, but actual, present-day liquid lakes that Cassini's radar mapped in extraordinary detail over years of repeated flybys. But none of these discoveries, remarkable as they are, explain why Cassini's ending was planned the way it was, and the reason for that planned ending is itself one of the most ethically significant decisions NASA has ever made in the history of robotic space exploration. By 2017, Cassini was running out of fuel. After 20 years of operation, the propellant that the spacecraft needed to adjust its trajectory and maintain its orbit around Saturn was nearly exhausted, and once it ran out, mission controllers would lose the ability to steer the spacecraft at all. An uncontrolled Cassini drifting in the Saturn system posed a risk that NASA's Planetary Protection Office considered unacceptable. The possibility that the spacecraft might eventually crash into Enceladus or Titan, both of which had been identified as potentially habitable worlds. Cassini had been built before those discoveries were made, and it had been sterilized to Earth standards of the time, but not to the standards that would be required for a mission intentionally targeting a potentially life-bearing world. Somewhere on Cassini's surfaces or in its instruments, after 20 years in space, a small number of Earth microbes might still be alive, tougher and more resilient than anyone would have expected. If Cassini crashed into Enceladus and those microbes contaminated the moon's ocean, they could potentially confuse or destroy any future attempt to search for genuinely native Enceladian life. NASA decided they could not allow that to happen. Cassini had to be disposed of in a way that guaranteed it would never touch either of those moons, and the only option that made scientific, ethical, and practical sense was to fly the spacecraft directly into Saturn itself, where the crushing pressure and heat of a gas giant's atmosphere would vaporize it completely and permanently. The mission planners, faced with this final chapter, made a choice that elevated Cassini's ending from a controlled disposal to what they called the grand finale, one of the most scientifically productive phases of the entire mission. Beginning in April 2017, 5 months before the final plunge, Cassini was redirected into a series of 22 orbits that nobody had ever attempted before, and that nobody will ever attempt again with Cassini's particular suite of instruments. Each of these orbits carried the spacecraft through the narrow gap between Saturn's innermost ring and the top of the planet's atmosphere, a region roughly 2,000 kilometers wide that had never been directly explored by any spacecraft in history. Nobody knew with certainty what was in that gap. The ring particles that might be present could potentially damage or destroy the spacecraft on the very first pass. Mission controllers pointed Cassini's large dish antenna forward like a shield on the first dive, using it as protection in case of particle impacts, and held their breath. The spacecraft survived. All 22 dives were completed, and the data that came back from those passes was extraordinary. Cassini measured Saturn's gravity field with unprecedented precision, allowing scientists to probe the internal structure of the planet and determine how deep the giant wind systems visible on Saturn's surface actually extend. The answer turned out to be deeper than expected, with Saturn's powerful jet streams reaching thousands of kilometers below the cloud tops before merging with the planet's interior. The spacecraft sampled material in the gap between the rings and the planet for the first time, discovering fast-moving molecules and particles smaller than 2 nanometers streaming from the innermost ring into Saturn's atmosphere, a process that helps explain how the rings are slowly losing mass over geological time. Cassini measured Saturn's magnetic field at closer range than had ever been possible, revealing something that genuinely puzzled planetary scientists, because it breaks a rule that every other magnetized planet in the solar system follows. Saturn's magnetic field axis is almost perfectly aligned with its rotation axis, to a degree of precision that current physics cannot adequately explain, because current theory says a slight misalignment between the two is necessary to sustain a planetary magnetic field at all. Saturn is doing something that, according to our best models, it should not be able to do, and Cassini's grand finale brought scientists close enough to measure exactly how precisely that impossible alignment holds. And then came the last orbit. On September 9th, 2017, Titan drifted past Cassini at a carefully calculated distance, and the moon's gravity gave the spacecraft a gentle final nudge that changed its trajectory permanently and irrevocably, pointing Cassini directly at Saturn on a path from which there was no return. 6 days later, the spacecraft made its last approach. On the evening before the end, September 14th, Cassini took its final photographs, a last look around the Saturn system it had spent 13 years exploring, including a parting image of Titan veiled in its perpetual orange haze, and a view of Enceladus sinking behind Saturn's limb, 2 worlds it had transformed our understanding of, 2 worlds it was now protecting by choosing to die rather than risk contaminating them. The imaging cameras were then switched off because their data could not be transmitted in real time during the final plunge, and Cassini reconfigured itself for its last act, orienting its ion and neutral mass spectrometer directly into the direction of travel, positioning it to taste the atmosphere of Saturn as the spacecraft descended, and linking its antenna as directly as possible toward the distant blue dot of Earth. The final descent began in Saturn's night side, at a latitude of about 10 degrees north, and took place at a speed of approximately 70,000 miles per hour, roughly 113,000 kilometers per hour. As Cassini first encountered Saturn's outermost atmosphere, the spacecraft's attitude control thrusters began firing in short bursts, working constantly to push back against the thin gas drag and keep the antenna pointed toward Earth. The thrusters started at 10% of their capacity, and it began climbing as the atmosphere thickened around the spacecraft. For the first minute of atmospheric contact, Cassini held its orientation. The data kept flowing. The ion and neutral mass spectrometer kept sampling the composition of an atmosphere no instrument had ever directly tasted before, measuring hydrogen, helium, water, methane, and a range of complex organic molecules present in Saturn's upper cloud layers. The magnetosphere instruments kept reading the electromagnetic environment around the spacecraft. The radio science system kept transmitting, its signal carrying not just data, but the information encoded in how the signal itself was bent and shifted by the atmospheric gases surrounding the spacecraft, telling scientists about the density and composition of each layer Cassini was passing through. It was, as National Geographic described it in real time, behaving like an atmospheric probe, breathing in as much of the alien atmosphere as it could and exhaling data as quickly as it inhaled. The thrusters reached 100% capacity. They could do no more. The spacecraft, still intact, still functioning, still transmitting, began to tip. The atmosphere had grown too dense, the aerodynamic forces too powerful. The battle between Cassini's thrusters and Saturn's sky finally decided in Saturn's favor. In its last 8 seconds of stable transmission, Cassini sent back one final burst of data from sensors that were still functioning, still reading, still witnessing the planet even as the planet was consuming the spacecraft. And then the antenna tipped away from Earth, the signal died, and Cassini's transmission ended. It had survived 91 seconds inside Saturn's atmosphere before the planet took it. Within seconds of losing signal, the spacecraft broke apart. Within minutes, it had vaporized entirely, the atoms of its metal and glass and wiring dispersing into the clouds of a world it had spent 13 years studying, becoming, in the most literal sense, part of Saturn forever. In the control room at JPL, the monitors went flat at 7:55 in the morning, but everyone present already knew that the spacecraft had actually been gone since 6:32 a.m. Pacific time, because the signal that just died had left Saturn 83 minutes earlier. The grief on those faces was real, but it was grief for an event that was already history by the time they witnessed it. The spacecraft they loved had died alone, surrounded by the atmosphere of Saturn, with no human being anywhere within 1.5 billion kilometers, and the last thing it did with every remaining joule of power it possessed was point its antenna toward a pale blue dot and transmit. It never stopped working. It never stopped sending. Right up until the atmosphere physically overpowered the mechanisms keeping it stable, Cassini was doing its job. What those final minutes of data revealed, and what the years of subsequent analysis have continued to extract from everything Cassini sent back, is still being actively studied. Scientists confirm that Saturn's rings are dramatically younger than the planet itself, likely no more than 100 to 200 million years old, meaning they formed long after the dinosaurs were already walking on Earth, almost certainly from the destruction of a captured moon or comet that wandered too close to Saturn and was torn apart by tidal forces. Saturn itself is approximately 4.5 billion years old. Its iconic rings, the most recognizable feature of any planet in the solar system, are a relatively recent addition, cosmically speaking, and they are slowly vanishing, raining onto the planet's atmosphere at a rate of thousands of kilograms per second. Cassini's grand finale measured that rain directly, confirming that within 100 million years or so, Saturn's rings as we know them will be gone. Future civilizations, if any exist, may live in a solar system where Saturn looks very different from the planet that has defined our mental image of it since the invention of the telescope. The discoveries about Enceladus and Titan have not faded with time. They have, if anything, grown more significant as scientists continue analyzing the data Cassini collected. The presence of molecular hydrogen in Enceladus's plumes, combined with the detection of silica nanoparticles that can only form in hot water reacting with rock, has made the case for active hydrothermal venting on Enceladus's seafloor as strong as any indirect evidence in planetary science. Multiple mission concepts are currently in development at both NASA and ESA to return to the Saturn system, and this time to specifically target Enceladus's plumes with instruments capable of searching directly for complex organic molecules, amino acids, and potentially even biological signatures. The question Cassini asked and could not fully answer, whether anything lives beneath the ice of Enceladus, is now one of the central questions driving the next generation of outer solar system exploration. There is a particular kind of loneliness to the way Cassini's mission ended that is worth sitting with for a moment, because it captures something essential about what it actually means to explore space with robotic spacecraft. Cassini flew for 20 years. It crossed the solar system. It orbited a ringed giant world for 13 years, swinging around a planet that no human being has ever visited and that no human being will visit in any of our lifetimes. It flew alone through a gap between Saturn and its rings that no machine had ever entered. And it died alone, burning up in an alien atmosphere with nobody there to witness it, transmitting data to the very last fraction of a second, because that is what it was built to do. The scientists who built it, who flew it, who spent careers listening to its signals, who watched the line go flat on a monitor in Pasadena on a September morning in 2017, were not there with it. They were 1.5 billion kilometers away, waiting 83 minutes for news of something that was already over. And yet the data came back. All of it. Everything that final plunge could capture, everything the instruments could measure, every chemical signature in Saturn's upper atmosphere that the ion and neutral mass spectrometer could taste as the spacecraft descended and burned, all of it crossed the solar system at the speed of light and arrived in the Deep Space Network's antenna in Canberra, Australia, where human hands had built a receiver specifically to catch this transmission from a dying spacecraft across an incomprehensible distance. The last thing Cassini ever did was teach us something. The last data it ever sent told us things about Saturn that we could not have learned any other way. And in a very real sense, Cassini did not end on September 15th, 2017. The data is still being analyzed. Papers are still being published. The discoveries are still accumulating. A spacecraft that vaporized into Saturn's clouds 7 years ago is still, through the data it transmitted, changing what humanity knows about the universe it inhabits. That is what those 91 minutes were. Not a death, not a failure, a final extraordinary act of a machine that, in the only way available to it, refused to stop doing its job until the physics of a gas giant planet made it physically impossible to continue. And even then, for 8 final seconds, while it was already tipping backward into its terminal tumble, the data kept coming.